it's a good group tonight, and we've got, I think, an excellent speaker. The announcements are that the observatory is still a little bit off limits as far as public events, as far as our stargazers. But that doesn't stop astronomy. And some of you probably, any of you know what's happening tonight? Everybody at once?
Orionids? No, they're done. Sorry.
Yeah, no, exactly. They're still going. And the Orionid shower should be good. And I think the moon sets about midnight. So after that, if clouds permit, there may be some nice fireballs. The Orionids are known for their fireballs. So that's rather interesting. Anyway, that's something to look forward to. And if you're wondering what's behind me, that's development of the dark matter between galaxies. As simulated by slime molds. And people are having a lot of fun with slime molds these days, putting them out and tailoring their environment to attract them and let them solve problems. So it's pretty straightforward how they solve mazes. But to work out distribution in 3 dimensions, or the traveling salesman problem, it's a pretty cool thing that's done.
Yeah. And
they really are sort of slimy, and there are about three classes of them. Some have individual cells. Some of them have one cytoplasm and 1,000 nuclei, something like that. So they're crazy little creatures. We've got a great speaker. I'm looking forward to his presentation. So I want to turn things over to our Vice President and Program Chairman, Don Spong.
Okay, well, we're fortunate tonight to have Bob Compton with us again. He did our January program, and tonight he's going to talk about exotic molecules, ions, and vacuum and interstellar space. Bob was born in Metropolis, Illinois, which actually is the fictional home of Superman. His family moved to Oak Ridge in 1943 during World War II, where his father worked at the Y-12 plant on the Manhattan Project. He then got degrees in physics from Berea College, the University of Florida, and then his PhD from University of Tennessee. Bob, in addition to his academic honors, Bob also has some interesting achievements in athletics. He was awarded the Athlete Scholar Award in 1958, the Athlete of the Year Award in 1959, and he spent 1 summer working at Y-12 and 3 summers at K-25 when he first got started. He became a senior corporate fellow at Oak Ridge National Laboratory from 1965 to 1995. And has been a professor of physics and Ziegler Professor of Chemistry at the University of Tennessee until his retirement in 2015. He's also been a visiting professor at the University of Aarhus, University of Paris, and the FAM Institute in Amsterdam. In 2001, he was Erskine Fellow at the University of Christchurch in New Zealand. And as an Erskine Fellow, he presented 8 two-hour lectures on the Manhattan Project to the city of Christchurch. He's a fellow of the APS, AAAS, and OSA. He's also received the Beams Award from the American Physical Society and the Megers Award from the OSA. So his research interests are in negative ions, laser spectroscopy, and molecular chirality. He has outside interest in music and trout fishing. So without further ado, I'll turn this program then over to Bob.
Okay, can everybody hear me? Well, thank you very much for inviting me to speak. David wanted me to talk about one part of what I'm going to talk about tonight, and Don wanted the other. So I'm going to be talking about 2 things that they're interested in, but maybe some others that you're. I'm going to try to put together some parts of the talk that impact on Oak Ridge National Laboratory while I was there for 32 years, actually. And in particular, I'll start off by talking about something called a buckyball. Maybe you've You've seen one of these before. These are carbon clusters. Every vertex here is a carbon atom, and there are 12 5-membered rings and 20 6-membered rings. These are closed hexagons, closed polyhedra of carbon atoms. And it's got a very interesting story, and it's connected with astronomy, actually. Many people were looking at something called the diffuse interstellar bands, and I'll get started on my talk in just a minute. But the buckyball really came about from the interest of astronomers and microwave spectroscopists in particular. Let's see, I need to share screen here. I'm going to talk about exotic molecules, of which C60 is one of them, and ions, particularly of C60, but other things. And then I'm going to go into something, and I've been involved in a lot of research in this area. And then I'm going to go to an area that I do not know much about, but I've been studying it for now 20 years, and it's the vacuum in interstellar space. And what is the vacuum? And so we'll get to that, but I hope I might have to throw out some of this in order to get to this, but I want to get to the vacuum in particular. So what is the interstellar space? I'm bringing coals to Newcastle here. You know more as much about this as I do. In astronomy, the interstellar medium is that matter and radiation exist in space between the stars and the galaxy. About 99% of material in interstellar space is gas. The other is 1% dust, with roughly 90% of the atoms in the gas being hydrogen, 9% helium, and 1% heavier elements. Of course, all of this, the carbon that's in part of this 99% of the interstellar gas was really generated in stars. And so we're going to talk about that. And interstellar space has an average density of 1 atom per cubic centimeter. That's pretty rarefied. Although there are regions with higher densities, like nebulae, that have millions of atoms per cubic centimeter. Also, there's a few electrons per cubic centimeter in outer space. And of course, there's photons in there. So astronomers have been looking at the stars since the beginning of time, really. And some of them having monochrometers can actually, there's something going on I don't know about. Anyway, so if you disperse the light coming from these stars and come up with a spectrum, it was early seen by Mary Lee Hager in 1922 that out of all this spectra that's coming in, some of it could be identified as atomic lines, hydrogen, whatever. But then there's a lot of lines here that are bands, really, that could not be explained. So this woman, Mary Lee Hager, in 1922, in the spectra of astronomical objects in the Milky Way and other galaxies, they are caused by light absorption by the interstellar medium. There's about 500 bands, or maybe more than that now, I haven't kept up with it that much, have been seen in ultraviolet, visible, and infrared wavelengths. Is there a question, somebody? Okay. However, there's been no agreement of the bands were found with laboratory measurements or with theoretical calculations until two groups discovered bands due to C60 and C70. So I'll get to the story of C60 and C70 and C60 plus in the next transparency here. So this buckyball that I just showed you are named for the geodesic domes of Buckminster Fuller. They're new allotropes of carbon, aside from graphite and diamond, and they're made of hollow carbon cages, C60, 70, 76, 84, and this goes on up. In fact, C20 is also one member of this. C60 has 12 5-membered rings and 20 6-membered rings. And you can talk about the geometry of these polyhedra from Euler's famous polyhedra formula. Euler is probably my favorite mathematician. Of course, he had his famous equation, e to the I pi plus 1 equals 0, probably his most famous equation, but this is also his polyhedra formula. The number of vertices plus the number of faces is equal to the number of edges plus 2. And when I was teaching physical chemistry at UT, I would have the students derive that formula. It's kind of cool. C60 and C70 were first made by laser ablation of graphite using a method devised by a friend of mine, Mike Duncan, at Rice University at the time. Now he's at University of Georgia. His machine was first used by Don Cox at Exxon and Andy Caldor to report C60 and C70. They actually did that. Did laser ablation of graphite, and then in a mass spectrometer, they saw these ions. And Harry Kroto in England came over to Smalley's lab knowing about this device they have for laser desorption ionization. And he came to Rice through a friend of his there, Bob Curl, which you'll meet in a moment as well. And he was interested in carbon clusters as an explanation for these diffuse interstellar bands. So he convinced Rick Smalley to let him use that machine for a week. That's all Rick was going to let him use it for, was a week, and to see if he could come up with these C60 and C70. As I say, Don Cox, a friend of mine at Exxon, had already seen this, but theirs wasn't as evident as it was when Jim Heath, a graduate student now at UCLA, actually did the experiments and they saw these two ions, and sort of the rest is history. When I first learned about it from Rick Smalley before it really got popular, I took some of this material that was coming off of laser ablation graphite on a plate and took it to Bob Heddick at Oak Ridge National Laboratory, and we did the mass spectrum here. And here you can see C60, C70, and the higher fullerenes as well. It really shows up beautifully if you let the other carbon clusters sort of land wherever they want to, and you pick this. But at the same time, we saw almost for the very first time a doubly charged negative ion. And I don't have time to go into that, but that's sort of one of my fields. I did a lot of work starting off with doubly charged carbon clusters, and I made a career out of studying doubly charged ions. We won't talk about that today, but I point this out as an illustration of what happens when you hit a laser on a surface and produce these carbon clusters. Let me pull this down a little bit. So here is the final result of that work there at Rice University was a Nobel Prize for Harry Kroto and Bob Curl. They were both infrared and microwave spectroscopists, and they knew each other very well. And so Harry came over at Bob Curl's invitation, and they worked on this machine of Rick Smalley's. The graduate student did the work, and so the result of all that was a Nobel Prize for these three gentlemen right here. How does these buckyballs get started in space? There's a lot of contention. Is it from the bottom up or from the top down? And so there's two schemes here that you can see of how these fullerenes, buckyballs, might be generated. So there's a lot of work out there in the literature, which I'm not really all that aware of. It's in the astronomy literature as well. In fact, there's one paper that claims that silicon plays a role. You have a silicon shell around these carbon clusters, and it closes in and makes it form the C60. That's a speculation, but everybody can speculate. So the net result was, and after they saw this, then people got really interested. You can do infrared absorption spectra of these fullerenes, and you could do a spectrum of them. And lo and behold, when you look out at the night sky and you do a spectrum analysis, what pops out is a number of these diffuse interstellar bands are due to C60, the red line here, and the blue line is the C70. So you can see clearly even the shoulder on this line right here. And because of the broken symmetry in C70, there's more lines to pick up, and you can see them picked up here. So there's no doubt that C60 and C70 are out there, and a lot of it too, in order to be able to see this. It wasn't until a few years later that John Mayer and his group in Basel, they discovered the C60 plus. In fact, there's a lot more C60 plus ions in the interstellar medium. And it represented a 20-year effort. This is quite an experiment. They take C60 in a trap at a low temperature. They let it cool down to 5.6 degrees K, and then it picks up a helium atom, and then they shine in a laser that breaks up the C60 and the helium. So in the mass spectrum that they're looking at, they see C60 helium plus, and then they, upon absorption of a photon to dissociate that, they see a C60 plus. And therefore, they were able to get a spectrum of the C60 ion at 5.6 degrees K. The helium doesn't do much to the vibration. It keeps it about the same. So here's what they saw. Now, this is an electronic absorption. There are two of them. And both of these are known. And you can see that falls right on top of the diffuse interstellar bands. This is perfect. You can see that the experiment is 9,632 angstroms and 9,577. So it's accurate to about 5 places here, which is very good. Later, in a later paper, they also attributed these two to also to C60 plus ions. That also means, since this is in the electronic spectrum, they must be in the vibrational spectrum as well, somewhere in here. And that still hasn't been done, but it's probably being done as we speak in some regard. There's another part of this story, and that has to do with Don Huffman and Wolfgang Kretschmer. They were also at the same time considering these carbon clusters, and they had a single line NMR of the C60 that they had done, and they actually made the C60 and C70 by arc discharge and make gram quantities of it. And you can see then they use something called a Soxhlet extraction. Since I'm not a chemist, I didn't know what that was, but I found out later. And they can separate the C60 and the C70. So here's a C60, which is a bright magenta color. And there's a little poem up here that's out there. It says, they seek it here, they seek it there. They seek that magenta buckyball everywhere, but space is full of high energy photons too. And so it is ionized and it has changed its hue. So somehow the C60 out in space gets ionized, and most of the C60 is in fact ionized. I think people have pretty much concerned themselves with that. And I'm pointing out another possibility. Instead of UV photons ionizing, that maybe it's being ionized by something called CW laser ionization of C60 using a normal low intensity light source to ionize the C60 through what we call thermionic emission. You just absorb enough photons in the C60 that eventually it reaches the point of dissociating the electron away and leaving the ion. Here's an example of what we thought was pure C60 in the mass spectrum using a very weak CW argon ion laser. And at low intensities, the C70 is bigger than the C60, which means there must have been a little bit of contamination in this. It means the cross-section for this thermionic emission for C70 is a lot bigger than for C60 is. So as you go up in laser power, you see what you expect. And in fact, you can ionize almost every C60 in the beam right here. This technique of thermionic emission was used by a group in Austria to do the double slit experiment. They used a weak laser behind the double slit and ionized every C60 that came through their slit, and it allowed them to do the double slit experiment. So that's a famous experiment that's out there. You probably know about that. So here are the,
Bob?
yes, please.
Quick question, Ted here. I thought these things looked like soot. So presumably your colored solutions are actually solutions in some solvent.
Yeah, that's right.
Very dilute.
You can take an art discharge. In fact, when I learned about this from Don Huffman, I'll tell you about him in a moment. He came to Oak Ridge. When I learned about that, I went down to Sears on a Friday and bought a arc discharge, an arc welder, I should say, an arc welder. Then I built a little cell that I could take two carbon rods and butt them together with an arc welder. And you make this, it looks like soot. And then you pour toluene or some solvent through there, and you'll get this. It'll be a combination of magenta and red, but then you can do the Soxhlet extraction to separate these. That's what I've done in these two right here. So these are separated. Does that answer your question?
Yes, thank you.
But it mostly looks like soot. You're right. Okay, there's a lot more I can say about that, but so this sort of solved one of the the first real evidence for these 500 bands in the diffuse interstellar bands. And I like to quote this thing here from Bill Klepper at Harvard University, who some of you might know. He said, "There's no better way to lose a scientific reputation than to speculate on the carrier of the diffuse interstellar bands." And Harry Kroto says, "Unless you're right." So he was a good friend of mine. I spent a few days in his lab there in Essex, and I've been in communication with John Mayer recently over the internet and et cetera. And Don Huffman came to my labs in Oak Ridge shortly after this. And I might say in confidence that Don, at a dinner party at our house one night, he sort of was ruminating, and he felt that he should have been a member of that group, and had Kratchmer maybe as well on the award. So he was pretty disappointed by it. But you know, there's every PhD or Nobel Prize has a story to tell. So we did a lot of work at Oak Ridge. I got an LDRD with Dave Gohegan at UT ORNL just before I left, pretty much. And we did, I think there was close to 80 publications came out of this work together. We did, here is Eve Klotz with the thermionic emission, this buckyball right here. I won't go through all these, but all these guys came. Alex Pretsy came over from Russia. He's now part of the, has been a part of the CNMS at Oak Ridge for quite some time. There's Phil Brett, now division director at Oak Ridge, I think, in chemistry. These guys did some hydrogenation. This guy, Philip Blau, did some work on the lubrication properties. This guy did a lot of work with me from China, from Jilin University, Dajun Ding, and he is now president of the Chinese Physical Society. I won't go through all these guys, but everybody has a story to tell here. Well, I'll tell this one. George Vignall and Kathleen Affolter did the first small angle neutron scattering on buckyball, and came up with the size. Not that anybody was surprised at the size, but you know, you got to measure something as an experimentalist. All right, let's turn our attention to another species that's out there in space. It's a little more close to home than what I've done in my past research. And that is dipole-bound anions in the diffuse interstellar bands. There's a case for that, and there's a lot more work ongoing in that. The first observation of a dipole-bound anion was made by Eve Klotz and myself at ORNL. And basically, what is that? That's a case where a molecule which has a large enough dipole moment, and this is CH3CN, that's the first one we saw. Then the electron is on the off on the positive side of this dipole, and you form a very weakly bound anion. The first calculation was done on Fermi in 1949, I think it was. In 1960, there was about 6 papers coming out with a minimum dipole moment required to bind an electron to a dipole. And so that was a big letdown when they found out that Fermi had done this in 1949. I'll show you a slide in just a moment about how that came about. Ray Garrett came along at Oak Ridge, and he showed that for a real molecule that rotates, it really requires more like 2.5 dBi for in order to form a bound state that would live for any length of time. Jim Turner did a nice study that went up to Chicago and got Fermi's notebook. And right after December 31st, right after Christmas, he worked out this problem. It's kind of interesting. The next page shows a long division. They didn't have calculators back then, so we had 2 pages of long division to come up with that minimum moment dipole. We've done a lot of work at Oak Ridge at using Rydberg charge exchange to form these dipole-bound anions, and you can do field detachment to get the binding energy. In fact, we published, among many papers, we published a PhysRev letters showing that you could even see the difference in the dipole moment between a deuterated and a non-deuterated acetone molecule. This is it here. Another example of this question about the diffuseness of these electrons. This is the HCN minus ion. We did that in 2009, and Ray Garrett and Bill and Sean Ard, who's now at the Naval Research Laboratories. The point is here that if you take this dipole, let's say it's in the J equals 0 state, and this diffuse electron is sitting out here, there's a severe breakdown of the Bohr-Oppenheimer approximation. You normally say that the electrons are moving fast compared to the nuclei, and so they can keep up with anything that happens here. But in this case, if the molecule rotates with J equal 1, it's barely bound, and J equal 2, the electron can't keep up with the dipole and it flies away. However, if you have a molecule with a bound state and then a dipole state, which is take a one electron away from the CH3CN, acetylnitrile that I showed earlier, where Klotz and I did at Oak Ridge. You can see an absorption between the bound state and this diffuse bound state up here. And so what they did was they showed, or Peter Saar in Birmingham, found a nice feature with regards to the bound state of the CH2CN minus ion. And I'm sure there's a lot of these out there. They just need to have a lot of more research, both in the lab. I think the experiments in the astronomy are already there. You just need to do these somewhat more difficult experiments in the lab to get these overlaps. And I might say there's also quadrupole bound anions, which Ray and I both have worked on. And I suspect that they will have even more import to this question of the diffuse interstellar bands. But nevertheless, at least 3 molecules are now well known to be in the diffuse interstellar bands. All right, let's take up a question that Dave Fields wanted me to go over again. I talked about this last January on chirality in the universe and on Earth. And there's a big question, it's been around for a long time. Why are we, human beings and most other animals, the amino acids, the proteins are made up of one type of amino acid. And we call that an L amino acid, and I'll get to that in just a moment. And I'm going to ask the question, did interstellar space send L amino acids to seed life on Earth? Big question. So you have right and left-handed amino acids, and we sometimes call it L and D or R and S. It depends on is it conformation exactly. And you can have little l and little d, which means which way it rotates the polarization of light. I went through this in great detail in the meeting in January, so I won't go over it again. But when I was preparing this book with Mike Duncan at Georgia on laser experiments in chemistry and physics, we had a chapter on subjects similar to this. And I found out that microwaves are known to racemize enantiomerically pure. Enantiomerically pure means equal numbers of right and left-handed. Enantiomerically pure means that you have only one of these enantiomers, either this one or this one. And microwaves excite a vibrational level followed by quantum mechanical tunneling through the barrier using circularly polarized microwaves, maybe a racemic mixture, could be made almost I'm getting too fast with my speaking here. Let me back up and say, if you take the potential between these two right and left-handed molecules, you have this barrier, okay? And you have vibration levels in that barrier. And you have rotation levels on top of that. And it's well known that if you take an R molecule, this one let's say, and you excite it with circularly polarized microwaves, it will quickly racemize. It'll give you both equal numbers of these right and left-handed molecules. Okay, I'm going to slow down a little bit so I can keep up with myself. So my theory is that if you come in with circularly polarized microwaves, you come up here and you could go from left to the right and separate this R and S mixture into one of these, either the RS, depending upon whether you use right or left circularly polarized light. And let me go back and say that I spent a lot of time in my 20-year career at UT studying the chirality of biomolecules, and I've done a lot of work in this area using circularly polarized light and all kinds of technology, including using microwaves and other things to study the chirality of these molecules. And anybody's interested, I can send you this book chapter. It's, what is it, 50 pages or so, 55 pages. I could send you this if you're really interested in this. I haven't done a very good job in explaining this, but just think of it this way. If you had circularly polarized microwaves with L and D, R and S molecules, which are made in the, if you just take a discharge of molecules containing carbon and nitrogen and other molecules, we know from the Miller experiments of the 1950s that you get these amino acids being made. Essentially now we know all of the amino acids are made with the discharge of these gases. And if you, let's say that you have these in space, and if you could have circularly polarized microwaves out there, you could induce one of these to go to the other. Now I did a lot of work using linearly polarized light to, and circularly polarized light to go from a right to a left-handed molecule, but you're chewing it up, you're breaking the molecule apart, you're doing photodissociation, and yeah, you can get an enantiomeric excess over time, but you're killing off both of them at the same time. So at the end of all that, you have nothing left. With this idea I have here using circularly polarized microwaves, you could excite this mixture, this RS mixture, with circularly polarized microwave and end up with either this one or that one over time. And so that's my hypothesis. I put this out in this book chapter that, chapter 31 of a book that Mike Duncan and I wrote on laser experiments. And we'll see if anybody picks up on that. It'd be a simple experiment if you have circularly polarized microwaves. There's some evidence for this, I think. Is there circularly polarized microwaves in outer space? The answer is yes. The Cat's Paw Nebula, and there's others located here 5,500 light years from Earth in the southern constellation of Scorpius. And let's see what else I've got here. They discovered that 22% of the cat's paw was circularly polarized. Isn't that amazing? And furthermore, they have taken, there's two meteors that landed on the Earth that have an excess of L amino acids over the D amino acid. And one of them was in Canada, the other's in Murchison meteor. This was the first one that was observed. And look at this, it's quite amazing. This is normally if you just made this aspartic acid, you would get equal numbers of these. This would be like this, but over time in the interstellar space, you have this buildup of one over the other. And the L is bigger than the D, which is what you want for life. And you can imagine that when this meteor came in from outer space, there was some racemization just due to the temperature of these meteors as they plow through the atmosphere of the Earth. And so probably before it hit the Earth, it could have been all of the L-aspartic acid. So it's conceivable that these amino acids have been cooked by microwaves, circularly polarized microwaves, to end up with the one-handed over the other. And it's important to point out that the microwaves do not destroy the molecule. It simply converts one to the other through probably a tunneling mechanism through the high vibrational states of it. Now, I should say one more thing. One of the things that I worked on heavily at Oak Ridge and while I was in New Zealand as well, it's known by Peter Sverdfager. He's a very good friend of mine, does theoretical calculation. We've done a number of papers together. And he has found that the L amino acids are lower in energy than the D. And we published a paper measuring that energy difference, and it's about 10 to the minus 10 EV. That was the PhysRev letters many years ago now. And 10 to the minus 10 is so small, I can't see how, unless something else happens, that could ever occur to give you an enantiomeric excess. However, these molecules could exist in outer space for a long time. And if you wait long enough, theoretically, it's a theoretical problem. I suspect, based on that small number I was quoting you, it would take more than the age of the universe for the L amino acids to be lower than the D. But that's out there. That's one of the propositions. In fact, we've had meetings on this whole subject, and it's still an unknown.
Bob.
Yes, please.
Excuse me for interrupting. This is John Rather.
Yeah, John.
I wanted to understand something, and you may have just answered it. I'm not sure. I believe that you implied that you have to have a preferentially circularly polarized microwave in order to achieve the transition you're talking about. And so it's kind of pushing the accidental polarization back to the microwaves. instead of the product. And first of all, is that true? And secondly, could the fact that you just described, that you have a slight difference in the ultimate lowest energy, interact preferentially with that if you had an equal number of right and left circularly polarized microwaves? Could the selection develop afterward due to that difference in energy?
I haven't had a chance to think much about that, John, but I doubt that. It would take a particular circular polarization to affect the thing that I'm talking about. I didn't do a very good job of explaining that. I got kind of carried away with myself. But I don't think the difference in energy has been around for a long time. And like I say, when we published this PhysRev letters on measuring an energy difference, it was for a bigger molecule, and one had a bigger Z, which is important, which I won't have a chance to go into. But there has been a lot of interest in just waiting long enough for the lowest energy state to be occupied totally. In fact, there was a person at the University of Maryland, I'm thinking, I can't pronounce his name, it's Pomerunum, and he was doing just that experiment. He was taking a racemic mixture of amino acids, putting them in a liquid nitrogen container and setting them in his lab. And then every few months to a year, he would pull them up and measure the optical activity to see if he was seeing an enantiomeric excess. And he did that over a number of years. And unfortunately, he passed away. I don't know if anybody else is.
Well, I must say that Cyril Panamparuma was a very close friend of mine.
Oh, really? Okay.
Yeah, he had dinner at my house about 2 weeks before he had his heart attack. And my own background in this topic is kind of incidental, but back when I was a graduate student in Berkeley, I worked with George Field, and we were looking at the collision of interstellar clouds, which is, of course, propelled by, say, ultraviolet from newly forming stars. And it's surprising that because of the extremely low density in these clouds, the atomic density is a few atoms per cubic centimeter at most. But the shock wave develops when two clouds collide at on the order of 10 kilometers per second. It's just barely moving by our standards. And so it's a long, drawn out, slow process. But if there's any ionization in there, and we deliberately put into our calculations carbon plus and sulfur plus and a few other things, and you excite the rotational states very easily, and lo and behold, this infrared emission propagates straight out of the cloud. It's not a black cloud for that. And the upshot is that it removes energy, cools the cloud, which forces it to collapse, and you develop a feedback situation where you get more and more of the ions into less and less volume, and it's a delightful mess that you can enjoy. But be that all of that as it may, my original question was, did you have to have pre-selection of the direction of circular polarization in order for everything else to come?
For my mechanism that I'm thinking about, yes, you would need one particular circular polarized, and that's apparently, that would be the case for these this cat's paw at least. There's other regions where circularly polarized light, and you could argue based on this, if there's other regions and other planets somewhere else in another galaxy far, far away or whatever, that the circular polarization would be in the opposite direction, or even in our galaxies, the opposite direction, so that the humans, if there are any that are in those planets, would be made up of D amino acids rather than L. There's no real reason for for the L acid. Unless this parity violating energy difference is really real. Even though I've been a proponent of it and I studied it very, very carefully, and it's in a lot of it's written up in this book right here, I'm not that encouraging that the parity violating energy difference plays a big role. So, okay. So let's go on to the last part of my talk here, the part that I had to spend some time on. This is not my field, but it's certainly my interest and probably yours as well. Let's ask the question, what is the space? Most of that in the interstellar space is vacuum, is space. It's created and is still being created by the Big Bang. And it just intrigues the heck out of me, as well as probably many of you. Let's start by saying that the Michelson-Morley experiment, they spent their careers trying to measure the luminescence ether, that medium in which light travels. So that was a big thing. And if you took a first-year graduate course or even an undergraduate course in physics, you know that their results were negative. They didn't see any medium in which carries the light. And so that at one point they were saying, well, this ether is carried along by the Earth as it travels around the sun and through the galaxy, and so you wouldn't see it there. But that probably not too, that was blown away when along came Einstein's theory of special relativity, and he explained why they would never see this perturbation to the velocity of light. So, however, this vacuum is not empty, and there's a quantum vacuum of virtual particles coming in and going out in accordance with the uncertainty principle, delta E, delta T of the order of H. I like to say, like, I've forgotten who the physicist was. I can't remember. He said, it's like borrowing money from the bank. If you can pay it back before you get audited, you can get by with it. So this is the delta E, delta T of the order of H. And these particles are coming in and out of existence. And there's evidence for this. Willis Lamb and Rutherford in 1947 used microwaves to determine the splitting between the 2s and 2p1/2 states. Your first course in quantum mechanics in graduate school is to derive the energy levels of the hydrogen atom, and you find that these are degenerate in energy. But they found when they did their microwave experiments that they have these two states are different by 1060 megahertz. A shift is actually now measured to 1057.864 megahertz. So Lamb and Rutherford made this experiment. By the way, Willis Lamb came through Oak Ridge. I can't remember when this happened. I remember hearing him give a talk or something, maybe met him, and he came through. His wife was not given tenure at Yale, and so he picked up and left. I think he went to Arizona. Somebody can correct me on that. So this Lamb shift is a result of the interaction between hydrogen and empty space. Along come Hans Bethe, and he did a calculation, and he got this self-correction energy to be 1,000 megahertz, very close to this value up here. And so he did this calculation and came up with this electromagnetic energy shift. And that was a famous paper of his. I should mention that Ted Welton, who was a friend of mine at Oak Ridge before he passed away, he actually may have been the first to do this calculation. In fact, he's done it in such a way that I could understand it myself. And you can find this on the internet and read his paper as well. It's actually something that I can understand. This is more difficult to understand, but he didn't get quite this number, 1,000. I think it was 500 or something like that. But he did that, and he told me, and I don't know if it was confidence or he told me at one time. I used to get together with Ted and Rufus Ritchie and Sam Hurst and I. We used to meet and talk about science and religion about once every 3 or 4 weeks for a number of years. We would meet at the Baptist Church or at the United Church in Oak Ridge, and I learned a lot from Ted and Rufus. Sam and I would sort of sit around and listen, but it was very interesting. And Ted said that after he left Los Alamos, he went back to MIT, and Victor Laskoff was there, and he had worked out this formula. I call it simple. It's simple because I can understand it. this simple effect that shows this fluctuation in the electromagnetic field. And Waskoff convinced him to hold off until Hans Bethe had his, so he was a year later, 47, 48. So he came in a year later. I like this example of the observed effects of the quantum fluctuation in the vacuum. It's called the Casimir effect. Most of you know about this, but I'll go over it again very quickly. It's also easy to understand, and even in a comparative way here. If you have two plates and they're close enough together that the energy levels of these vacuum states inside the plates are limited, and those on the outside are not, you're going to have a force that's going to slam these two plates together. It's called a Casimir-Poulter force. And this was measured by Steve Lamoureux at, I believe he's at Los Alamos, and he actually measured that. The people that did in the 1600s, the maritime people there knew about this effect in the sense that if you get two ships too close together, there's no waves on one side in between them, and the waves on the outside will cause them to crash together. And you might do that tonight when you're taking your bath in the bathtub. Your rubber duckies will coalesce together because of this. Let's talk about another way to maybe observe this effect in the vacuum. Most of you are familiar with the Faraday effect. It's the interaction of light with a magnetic field, and it's really Faraday was the first one to do this in 1846. And if you take a medium, he used a piece of glass, but take anything that's in here, and you put a linearly polarized light beam through this B field in the same direction, it will rotate the light right to the right or the left, depending on whether the material is paramagnetic or diamagnetic. And so a lot of people have been doing that. We do that as an experiment. And if anybody's interested, I have a big write-up on this in my book on laser experiments in chemistry and physics, chapter 21. I'll be happy to send it to you through the mail. And so that's the Faraday effect. Now the question one wants to raise is, can you see a Faraday effect in the vacuum? And that's a big question, and a lot of people are working on that right now. Magnetic vibration of the quantum vacuum is one of the most important predictions of quantum electrodynamics, which has not yet been verified. I've found at least 10 groups around the world who are attacking this problem. And so this is really a hot topic, even though you don't see much in the headlines because there hadn't been any results. But in fact, there was one result published in I believe that's a 6 right there, or 8 maybe. And this, I show this even though it was retracted a year later. I just want to show it to you to show you what people are doing with sort of LIGOs types of experiments. Really difficult. This is a difficult experiment. A lot of people have been working on this. This is a 20-year experiment. And it's a shame that they found some mistakes in their result, but that's what science is all about. Let me just give you an example. They use a B field, it's 5 Tesla, and they use 44,000 passes through this medium in here. And in the medium, it's 10 to the minus 8 millibar, or 10 to the minus 8 approximately torr. A torr is 0.72 millibar. And this length is 1 meter, and this is mounted on big rocks, big solid rock. And then this was rotated, this huge magnet. 5 Tesla is a big magnet, and they had to rotate that to do the experiment. They use circular. The actual reported rotations was 3.9 times 10 to the minus 12 radians per pass. So each time it goes through here, it does this kind of a rotation. The total number of rotations was 9.8 times 10 to the minus 6 degree after 44,000 passes through there. So it's really, this is the kind of experiments that people are trying to do right now in the lab to see this effect on the vacuum. And it's really as I say, I'll go back to this slide right here. There's just at least 10 groups which I can pull up. A lot of them are doing things like getting a lower vacuum. That vacuum of 10 to the minus 8 may not be enough. Just a few atoms or molecules in that vacuum may be enough to give you a rotation. And so that's a real difficulty of this experiment. So getting lower pressure, and also these windows that hold the gas in there, or the vacuum, the vacuum, they're working hard on that to keep them from becoming birefringent. When you particularly put a pressure, when you pump them down, the glass will bend a little bit, and you'll get a rotation just due to the glass itself. So there are groups just studying the windows. It may be that they'll have to do this experiment itself under vacuum, so that these windows will not be a factor in this. So this is really a difficult experiment. And I just wanted to point out that there's lots of experiments going on right now. I found at least 10. There's probably more, because that was like 5 years ago when I finally found that out. So let's see, I think I missed it. Yeah, let's go to this slide. So this is now, it turns out, by studying the light emitted from a very dense and strongly magnetic neutron star. So they're looking at light coming out from a neutron star. A team of astronomers has found the strongest observational indications yet of vacuum birefringence. That is, that the difference in speed of light for right or left circularly polarized light through the vacuum can be seen. So this is a strange quantum effect, first predicted nearly 80 years ago by Heisenberg and Euler, not the Euler, but another Euler. So this is an experiment that has been done. It's a little different from the optical rotation that I reported with the normal Faraday effect. And here's the artist representation of what's happening. Here's the neutron star. You know, a neutron has a magnetic moment, and they all line up, and you have this huge magnetic fields of the order of 10 to the 13th Gauss. This is an estimate, but that's a lot. And so here's the magnetic fields going around like this. Now, as the light that's unpolarized comes out of here, you'll have a polarization that's parallel to the magnetic field, and then out of the plane here, which is perpendicular. So as it goes through this magnetic field, this huge magnetic field, it will polarize itself. And in fact, they find a polarization of 16.43% from this neutron star. So that's quite an achievement, and it's the first evidence for it. And this was done in 2017. I wouldn't be surprised if there aren't more experiments that I don't know about. But anyway, this is it might take astronomy to solve this problem. Although, like I say, there's a lot of experiments going on around the world that's trying to understand this thing. I think I slipped the slide back here, and I wanted to get to it because yeah, I did miss a slide. I wanted to talk about this book. I've had this book for 20 years, and I've been studying it every year for a long time. It has 500 pages of difficult physics. I think Peter might be in the audience tonight. I asked him, I've been in contact with him, and I actually got him and Sam Faulkner together. I don't know if Sam is on the line as well, but Peter worked with Sam Faulkner at ORNL for a short period of time. Sam was my physics professor at the University of Tennessee in 1960. The first quantum course I had was from Sam, which I am happy to say that he convinced me to be an experimentalist. And so, and I had quantum mechanics and E&M from Sam there at the University of Florida. So I don't know if I showed this, can't remember whether I did that or not, but anyway, the fluctuations give rise to the energy shifts in certain energy levels in atoms, the Casimir force between plates, Hawking radiation from black hole, and vacuum birefringence. So we'll have to stay tuned. Maybe somebody can give another talk that's in this field on vacuum birefringence. It's very important. It'll rewrite Maxwell's equations to some extent, and it's one of those chapters in the story of what's in a vacuum. And so with that, I don't think I have anything else to say. Let me see if I have one more transparency down here. Oh yeah, I did find this paper here, which I found interesting. This is 1977. And future work, they're saying that the birefringence on the polarization of X-ray binaries and pulsars. I think this has a lot of possibilities because the closer you get in energy to the energy required to separate electron-positron pairs in the vacuum, the bigger this birefringence will be. And so X-rays will have a bigger polarization effect on the vacuum. And so this might be the next big thing to look for in neutron stars. In fact, in case it hasn't already been seen, I've done the best I can, Googling and whatever else, to look for anything. And maybe Peter Maloney has a comment to make on this as well. Well, anyway, thank you very much for inviting me. I enjoyed doing this, and I talked very fast. I hoped to get through in an hour, and I did. So I'm happy with that as well. So thank you very much, and I'll turn it back over to David.
Thank you, Bob.
Thank you, Bob. That was really neat. I guess there'll be a lot of questions. I was going back to the origin of the non-racemic mixture of the molecules just in our solar system. Let's assume it's from microwave radiation. What's the ultimate source of that circular polarization? Would that be the black hole jets?
I read about that. I don't think so, but I've read about that, and I've sort of forgotten the explanation that I read. I think it has to do with rotating electrons in a star, and maybe somebody else can correct me with that. But I should know that the answer to that. I did know at one time, and I've forgotten.
Bob, this is John Rather again. One crazy idea that occurred to me, of course, Faraday and many subsequent physicists have experimented with birefringence in material media, like crystals of one sort or another.
Started off with crystals.
And the media, of course, determine which way the rotation occurs. And so the Faraday rotation depends upon the molecular structure within the crystals. Now, since these microwave...
It requires the electronic structure, which way the electrons are going. But
Yeah.
anyway, yeah, go ahead.
Right. And so since we know that the dust, what we used to call the interstellar dust, is not simple stuff, it probably has a lot of fundamental molecular structure itself, and C60 is a perfect example. And as we know, there, what is it now, on the order of 65 different fairly heavy molecules that have been detected. So my point is that because the material itself can induce birefringence, then that may explain why there's a preferred circular polarization in the microwave background, and then that would lead to the everything else you've been talking about. Do you follow what I'm saying?
I do. I'm sorry that I can't remember because this is not my field, but so I read as much as I can. I know they understand the cat's paw circular polarization, and I don't think it has anything to do with that. I just don't remember the result. But anyway, I should also mention I did in one of my slides that there's about 50 electrons per cubic centimeter, or maybe a little less than that, in interstellar space, and they believe they have actually seen a rotation of the polarization due to those electrons, because electrons do have a handedness to them, and they will actually give you a Faraday effect. Those have been measured, and they think they have seen that in radiation from the black body radiation.
Yeah, it's ironic that the people who are trying to prove inflation, of course, are looking for circular polarization as an evidence of it. And one of the Nobel seekers prematurely announced that he discovered it. And of course, everyone who knew about what goes on with the dust pointed out that all the Planck data and so on fully accounted for what he had observed just from the interaction with the dust producing residual circular polarization. So
I hope everybody got my message about in the very beginning about astronomy really determined the buckyballs. I mean, that was the impetus for studying and finding buckyballs. And then I've also pointed out that maybe the program that I started with Dave Gohigan at the lab was the beginning of the CNMS because of buckyball. So buckyball ignited a lot of interest in a lot of different things throughout. So,
Hey, Bob, you mentioned the buckyballs. The C60s anyway in space are ionized. And there are a lot of electrons. It surprises me they don't fairly rapidly, maybe they're just not close enough, pick up those electrons. Now, is it because there's enough UV flux that they keep being ionized?
the answer is both yes. And it turns out, I published a paper on electron attachment to C60 many years ago. And it has a very unusual capture cross-section. It captures electron, not at zero energy, but from about 0.2 eV all the way up to 20 electron volts, unheard of in molecular physics. Usually you have a resonance at zero energy, it either goes up, or you might have a resonance at some higher energy, but never over that full range. And there are ripples in that, which we call plasmon resonances. But it has a big cross-section for attachment. I don't think that you would see negative ions in the outer space because the UV photons would knock the electrons off. And fortunately, the UV photons or the process that I talked about with you, clots, might be the reason that they're positive ions. But it's mostly positive ions in the interstellar space. Mostly positive ions, but there is some C60 and C70 neutrals as well. And you know, there's probably other species of C60. I mean, you can hydrogenate C60. In fact, one of my students was at UT, and now he's at Savannah River National Lab. He made C60H60 for the first time, so completely hydrogenated. When you do a computer program of it, it looks like a coronavirus.
So there is an organic chemistry based, or can be an organic chemistry based on various levels of C60 and other buckyballs.
Yeah. Yeah. Oh, yeah. It's I should mention another comment about the C60. I worked with a group at UT in the Environmental Sciences Division over there, and they were studying the environmental effects of C60. And so there was a big flap about 20 years ago coming out of Rice, of all places. And Rice was saying that this was Vicki Colvin down there at Rice, and she was claiming that you put C60 in water, the fish go backwards, and it was causing all kinds of, and it was really creating quite a stir in the community because maybe these nanomaterials, you hear the nano business all the time. And it turns out, working with this group over at UT, they found that it was not the C60 in the water, but it was the tetrahydrofuran that they needed to put in the C60 in order to get it into the water. And they didn't get this. They didn't get the tetrahydrofuran out. And apparently every environmental chemist knew that tetrahydrofuran was bad for the fish. But that paper got over 100 citations in about a month and a half.
Where was that work done?
That was done at UT. Ted Henry, who was the primary investigator over there. I was on the paper, but I didn't do much except to give him some C60 and consult with him. He's now at the University of Edinburgh. Yeah.
Glad it wasn't done in Australia, where the Coriolis forces come into various
Yeah, right.
pieces of equipment.
Yeah, right. Okay.
That's cool.
I'm wondering, what is it that gives the neutron star such a large magnetic field? You normally would associate large magnetic fields with moving charged particles, but is it the neutron magnetic moment?
That's my understanding of it. And, I was surprised that I floated this vacuum birefringence to my colleagues at UT, and they hadn't heard of this. So this vacuum birefringence is it's not that high on the burner. some, there are a lot of people working on it, but there's not a lot of people knowing about it. I was surprised that my colleagues at UT did not know about it. And I don't think I answered your question, but yeah.
We had one question come up. It was private comment, but the implications have to do with the fact we have buckyballs, which are more or less soccer equivalents, but nothing like American football. And is there some grand cosmic significance in that?
No. But somebody put a chat up here, which I think is very pertinent, that these neutrons inside the neutron stars, even though they do have a neutron moment, they're going around like crazy. They're spinning at some high rate. So that could be also the source of the magnetic field. So.
Well, the neutrons are bosons, right?
Yeah.
So they're going to all try to get the same.
Yeah, they in fact, that's why they coalesce so much. There's nothing to stop them from coalescing.
Right. You're never going to get an electron star like that. Would not
I think Ted Barnes might have had a question.
Sorry, got to find my unmute button. You covered such a wide range of topics. My head is kind of spinning.
Yeah, I know. I can imagine.
And all the years I've known you, I had no idea you were working on all these really interesting subjects. I don't know why we never talked about them. But I don't know specific questions. I have one that's kind of the stupidest and simplest of them all, which is I didn't know that buckyballs and their friends were purportedly a large fraction of the poorly understood radiation from the interstellar medium.
Yeah,
I had the impression from your talk it might be a large fraction, like 10–20% or something like that.
Well, I don't know that you can see the size of the intensities on the infrared spectrum there, and then you might be able to. You need to know about absorption cross sections, et cetera, to compare it with everything. But it's a large fraction, and what I found interesting in talking to John Mayer, who's the guy that did the C60 plus, that most of it is ionized C60 plus ions. And Croto and all of these astronomer types were kind of surprised at that, and so am I. I'm also surprised at it. I suspect that there's the rest of those 500 lines or so are due to carbon clusters of one type or another, maybe CN type clusters, and I'm very optimistic about the quadrupole bound anion states as contributing to the diffuse interstellar bands. And the reason I say that is that there's a lot more quadrupole molecules with quadrupole moments than with dipole moments among those that are out there. Maybe some CN molecules would have a large dipole moment, but the reason that these are of interest is that nobody knew about dipole bound anions until fairly recently, and they're just now beginning to study them. I was the first one to observe one of these in 1967 or whatever it was with Eve Klotz. So, we'll see. It's in a way it's kind of anticlimactic to come and measure another one because it's a lot of work to do these experiments to get low temperature spectra of ions. That was a major 20-year effort of John Mayer to see the C60 plus vibrational spectrum. So these are difficult experiments, and we'll see what other interesting species come out of this. I know John Mayer has retired, so I don't know if there's any people in his group that are doing any of this.
I do have one more quick question. This is another thing that may be a stupid question, but I'll ask anyway. When you were talking about making more complicated things, starting from a few carbon atoms and hitting another cluster of a few carbon atoms, is the building up direction. It occurred to me those, when they do happen, are inelastic collisions. And so you must be throwing off something like a photon when the step up in size of the cluster happens, right?
Well, these things,
Is there any chance of detecting those photons emitted in the formation process?
In the formation, that's a good question. You know, I don't know the answer to that. I know that there's a lot of spectra now that have been looked at in the emission spectrum, in the infrared, for example, with C60. But I don't know that anybody has really studied the spectra emitted from these buckyballs. They get very hot, as I say, they thermionically emit. So you have one photon hitting it, another photon hitting it, another photon. It just builds it up, and this buckyball here, this thing is just vibrating like crazy until it spits out an electron. Now, I find that an interesting phenomenon in itself. So there have been so many interesting physics problems that have come out of the C60 world that I could give a whole another talk on that.
In answer to Ted's question about the 20% population, I believe it's now pretty well understood that buckyballs are generated copiously in the atmospheres of red giant stars like Betelgeuse, and that you have enormous volumes in the late phases of stellar evolution where the production can probably be very efficient, and the buckyballs themselves may be another manifestation of lowest energy combination of carbon atoms, and so it's sort of the preferred product given that range of possibilities, and of course it all gets blown away into the interstellar medium as the star becomes either a white dwarf or a supernova.
Gotcha.
I would agree with that, but I would also say that these buckyballs are really very stable. I mean, I could drop this, although my wife would not like that, I could drop this glass buckyball that she made for me a number of years ago on the floor and it would probably survive.
So this is a molecular version of making iron in the star.
Yeah, right. That's right.
That's good, actually.
Hey, Bob, I've got a question. This is not such a deep question, but I was intrigued by your discussion when you took the plate that had on it the residue from doing the laser ablation,
Yeah.
and it had C60 and C120 and everything. As I understand it, you got these nice results. When you analyzed it, how did you mobilize this junk in your mass spec?
Oh, it's very easy.
Did you thump it with your finger, or
put it, you scrape some off, put it on a plate. It might help to put some, some toluene or something to get it to stick on the plate long enough to do the mass spec. But
so did you then heat it up and vaporize it? Or something?
No, we usually use a laser to desorb. It's laser desorption ionization, it's called.
Oh, okay. You kicked it out with a laser.
Yeah, you kick it off with a laser.
Okay, that's nice. That was conceptually simple, but it's really important.
It's very simple. It was really nice to have Bob Heddick there at the lab, who had this incredible mass spectrometer that we used to do this, because we could do resolution that the Rice group could not approach using his Fourier transform mass spectrometer. And so it was just a very, the biggest disappointment or thing that I look back on, and I missed it, I took some C60 down to Ray Zur, who was in the solid state division, and they had ion implantation that was left over from Bill Appleton. Bill Appleton did a lot of ion implantation in the solid state division. And I gave some of this to Ray, and he did a implantation of helium, so helium plus ions. And what we found was that almost all of the C60 had taken a helium atom inside. So you have a helium atom sitting inside this buckyball, okay? And I was just flabbergasted with that, and I didn't publish that. We should have published that because a lot of people are interested in these endohedral fullerenes. So it's just, I look back and I say, I should have done that, but I didn't do it. It's too late. But it's possible that a lot of the C60 that's out there has helium inside of it. I mean, it won't come out. It's bound thermodynamically and construct, can't get out of the cage. So I wouldn't be surprised if somebody found helium inside C60, because it's very easy for us to put the helium ions inside the cage.
The cage is big enough for a lot of other things, though, isn't it?
Oh yeah, you can put a lot. I published a book chapter on inserting atoms inside the C60, and you do that by not shooting ion beams in it, although you can with helium, as I just mentioned. But you can take and mix lanthanum or other metal atoms in with the graphite. You heat it up and bake it, and then you do the arc discharge with that, and then you find that you have a lot of endohedral fullerenes with metal atoms inside, and then you can study those. It's kind of interesting.
Can you observe the spectra of things like helium that are trapped inside the buckyballs?
You know, I don't see why you couldn't. We could make a lot of it, and so it would be interesting to see if you could see, you know, the helium lines coming out of a discharge of buckyball with helium in it, and see if it's different. You know, it might be slightly different in energy from the encaged. It probably push the energy up a little bit, I would guess, from the confined.
Yes, I think so, because it's definitely going to be rattling around inside there.
Yeah,
And yeah.
Yeah, it would probably be a little bit of a lift in the energy level.
Yeah.
I should
And crystal field splittings from the geometry of the surrounding field.
I should also point out that I got this LDRD money. Had to get down on my knees because nobody had heard about C60 at the lab, so I had to get down on my knees and cry to get the money. And we got that money, and you can see how many people benefited from that slide I had of the group that we had formed. And we also got a $15 million grant with Georgia Tech based on that work. And in fact, when I left the lab, I took part of that $15 million to UT, along with the lab gave me all of the equipment that I had at UT, to UT, and as well as the equipment at K25, which was part of the isotope separation program out there. So I really owe a lot to ORNL and K25 for setting me up really well at UT. And I had like 40 students at UT that are out there doing good. So that LDRD was probably, I would guess, one of the most successful LDRDs at the lab.
That's pretty impressive, Bob. Thanks so much.
Yeah, I enjoyed it.
I don't mean to cut off the discussion, but I'll say that in case you need to escape or something.
No, certainly enjoyable. Thank you, Bob.
Yeah, thank you, John.
Hope to see you again.
Okay,
Thanks much.
bye-bye.
Yeah, thanks for, I really enjoyed the talk. Thanks. I made notes and hope to look some things up.
Okay.
Peter, thank you so much for joining us. Your book comes up. John Rather mentions it occasionally, and of course Bob does.
Thank you.
So Ted, your scope is back in from England, and it's all set up and ready to go?
No, the company in England didn't reply at all, and apparently that's what they're like. It takes months and months before they finally admit that they have your mount. So they've still got mine. So I just said, okay, I've got some money. It's only money, and this is what it's for anyway. So I bought an upgrade. I've got a CGX mount now. And so I sort of had a crash course in learning how to use this new mount. I did several things wrongly, but last night I got guidance working, and it was actually guiding pretty well. And of course, a lot of my friends are bugging me about Mars. Send us a picture of Mars. You know, and I said, oh, it's only 20 pixels across for me. It's going to be pretty bad. And I don't have any way of stacking images of something round and floppy that's fluctuating. So they're not going to be very good. But I did take one, and I've also got one from another planet nearby. So shall I do a screen share and
Yeah, please
show
do.
you what I've got? Okay.
It's good. Only two things. It's daylight and it's inside, but it's pretty scope.
Yeah, and well, it's the same scope as before. It's the 8-inch Maxitov Newtonian with this low camera on it, but it's got a CGX mount, so I can actually point it in interesting directions now. Now let me see. Okay, well, I was going to say first I tried Mars, and then I went to another planet, but it looks like maybe it'll let me show the other planets instead. So here's one of them. You see anything now?
Yep.
Yeah.
Okay, any guesses?
Uranus.
All right, it's Uranus. And
I guessed that because of the file name.
so, yeah, very good. I should cover that up with my hand. So anyway, some fraction of these things are stars and some fraction are actual moons. It's kind of hard to tell which is which, so I waited a day and took another picture, and it looks like this. So now it's moved off to the right a ways. And what you can tell is that the three brightest white balls around Uranus are three of the brightest moons. There's I just made up a little way of mnemonic for them, which is Auto, A-U-T-O. So starting from the closest, which isn't visible here, they're Aereo, Umbriel, Titania, and Oberon. So the
Ted,
furthest
is
one.
it possible you use your pointer to point out the moons? All
Can you
the
see my pointer?
Yeah.
Yes.
Oh, you can see it. Okay.
yes.
So Ariel is actually in here, hidden in the glow. It shows up in another one of the pictures. The next one out here is Umbriel, and then Titania, and then Oberon. This is a background star. If you go back to the other image, out of curiosity, does the second image show up as well too?
Mm-hmm.
Okay, that background star, this is where Uranus is moved to in one day. And so that background star is it a moon or not? So you can see here, 3 of the 4 bright moons, bright meaning 14th and 15th magnitude. The only other one that I've got a chance at is Miranda, which is closer than Ariel. And in these two, you don't even see Ariel. Like I said, it's right about here. And Miranda is about 2/3 of the distance from the center of the disk of Uranus. So I'm going to try tonight to figure out how to get the disk smaller, so maybe I can see more of the thing. Pictures. We've on Mars. So that's my, oops, let me enlarge it. That's my best image of Mars. I'm sorry, it's not great, but you have to take such a fast picture to get anything that's not flooded out. That's 1/16,000th of a second. And you can see, okay, dark southern hemisphere and maybe a hint of a pole down here. And when I looked at the Mars globe, there is a place where, when you're rotating it around, where it looks like that kind of lines. Okay, but none of the really exciting famous features are on this side. And I could check that they repeat after a day, because fortunately I took the images from day before yesterday and last night apart by 24 hours and 37 minutes, just accidentally, which is bang on the rotation period of Mars. And the dark areas are the same in night before last and this one from last night. The one thing I learned is that some filters do help, like this has a Retin 25 red filter stuck in and does improve the contrast of the bright and dark areas.
Red 25, as I recall, is an extremely dense, deep red filter, very deep.
Yes, it is. Yeah. But
And it's one of the ones that I used to use when I was playing around with infrared film. It wipes out it leaves the infrared nicely. Yes, that's what I want to put it. So you see actual craters here in your picture? I'm trying to understand.
well, there's only 20 pixels going across there, so any hot pixel is going to look like a feature. So,
Nice.
and as I said, this is the one that seems to have the closest thing to real features in it. The others look typically a bit blurrier. So it would be nice if there was a way to stack them, but I just don't have a way to do that.
There is software to do that. I've seen demos on YouTube, although I haven't done it myself, so I couldn't remember the name of the program. So there's if you just look up like planetary stacking, you can find I know that there's 2 free apps out there that they recommend for that.
Okay, yeah, once the excitement fades and Mars gets further away, I'll see if I can find any way to do it. So I've got 5 sets of I think something like 50 images each.
Oh, good.
Just waiting to be stacked. Okay. I've got the raw materials. All right, so that's my images.
Thank you, Ted.
Sure.
Yeah,
Great.
yeah, thank you.